And now for the last talk of the day, Filippo Valsorda will speak about high assurance Go cryptography. Please welcome Filippo Valsorda.
Hi everyone, it's very good to be back in person. All right, so a bit about myself. I'm Filippo, and I've been at Google on the Go team from 2018 to 2022. I left earlier in May this year, and I am still maintaining the Go cryptography libraries as an independent professional maintainer. While at Google, I was in charge of the security of the Go distribution. Our job was to make sure that Go was and was perceived as a tool to build secure applications. So, you know, all those emails to Golang announced, well, that was the team I was on. And I mentioned professional maintainer. That's a whole other story, but in brief, I am still doing what I was doing at Google, still maintaining the Go cryptography libraries, which is what we're talking about today. But I'm trying to do it by, as an independent maintainer, to prove that it's possible for open source maintainers to build a career out of open source. But again, as I said, that's a whole different story. There's a link, and everything in this talk is going to be uploaded later, because this is a bit of a weird talk. We don't have slides. We'll be in VS Code the entire time, and we're going to jump around in the Go cryptography libraries to look at different things we do to make sure that they are safe. So now is the time to move to the front if, like me, you're nearsighted. Or to tell me if that's too small text to read it. Yes? No? Okay? Lots of space in the front, I'm not kidding. Okay, so Go cryptography libraries. Yes, yes, be like that man. The Go cryptography libraries, they are the packages in both the standard library and in the X repos that under crypto/ and under Golang.org X crypto. Most Go programs use them, if nothing else, when you make a HTTPS request. You're using crypto TLS, which uses crypto ECDSA, and uses crypto RSA, and everything in the stack, basically, every time you make a TLS request. And we're going to talk about things that we do to make sure that this, which is arguably the most critical, or one of the most critical code bases in the Go ecosystem, is free of bugs. Because almost any bug in cryptography is a security bug. We've tried multiple times to be like, I don't know, maybe that's not a fine, right. And so we need that to be safe, and the whole Go ecosystem relies on it. So what are the things we do to make sure that it is indeed as secure as we would like it to be? And we're going to talk about things like tests, which, you know, duh. And a lot of it will be a bit of Captain Obvious, but I want to stress how much effort we found pays dividends into each of these things. We're going to talk about fuzzing, we're going to talk about safe APIs, we're going to talk about code generation, formal methods, and then we're going to talk about things that are more structural, like complexity and the readability of your code. So let's get started. We're going to start by talking about test vectors, because sometimes the test vectors are there, and you just have to run them against the application. And in cryptography especially, where there are specifications that we have to implement, where we don't make up, I don't know, I think I want to make a signature and it should look approximately like this. It has some IETF spec or something like that. We have the opportunity to reuse packages, basically, of test vectors, like the one from the Google ISC crypto team, Whiteproof. Whiteproof is this project that has test vectors for all of these different cryptographic primitives, and they look all like this. They're just long files of JSON with, here's the inputs, the public and private input to a Diffie-Hellman computation, for example. And here is what the output should be. If it's invalid, it should return an error. If it's valid, it should return this thing. So these are your standard known answer tests. And we have this package in the Xcrypto repository, which just deserializes them and runs them against the the functions that should pass or not pass. So, a bunch of decoding, and then make the private key from the private value, and then run the thing. Check if it returns what we expect, biddy body boo, done. So that's what integrating Weichproof was like. Now, by the way, when I say we have, I'm talking about things that we do in the project. Some of these things I've done, some of these things I've reviewed, some of these things others have done. For example, the Weichproof integration was the work of Katie Hockman, who was working on the Go security team. And we have integrations for all the different things that Weichproof supports. And a thing that I think is neat about this package is that this is a test-only package. There is nothing in here, and these two files, I didn't remember them being here, so it kind of defeats my point, but imagine they're not there. Without those two files, the only files in that package are _test files, which is a thing you can do, turns out, and just works. You can run go test on a package that contains no code, basically, and it will still run in CI and still run the tests. And another neat thing we do in this package, I think, is that these are test vectors that we didn't write ourselves, so we fetch them from outside, which, by the way, is something I really believe in, the sharing test vectors between different implementations. And how we fetch them is that we use the Go tool itself. We use GoMod download to fetch the repository that you were looking at earlier, and we fetch it at a specific version. And so the modules mirror, the modules proxy, and the Go checksum database ensure that it's always the same and that the tests are reproducible. But we don't have to actually vendor them into the standard library because you saw how big they are. There are some megabytes worth of JSON. And we just GoMod download them with JSON and then go fetch the directory in which they were unpacked. Anyway, these are, these are tests that other people wrote for us. For other functions, like add to 5519, which is a signing function, we had to go and write our own vectors. Why? Well, add to 5519 is, I'm going to go with underspecified for political reasons. It doesn't really tell you what the function is supposed to do when the public key is a little weird. And you might say, well, the public key is something you should trust. If you're verifying a signature where the public key is not trusted, why are you checking the signature in the first place? Well, I'm told that there's these weird technologies that people call blockchains that have opinions about consensus or something. Well, they really have opinions about everybody agreeing on doing exactly the same thing when they try to do the same thing. So they have opinions on if we have a public key and a signature, everybody should agree whether this is valid or not. So what we did is that we ended up writing these very large test vector set that test all the different edge cases that are underspecified in the in add to 5519 and run them against the verify function and make sure that only the ones we expect to verify or only the ones that we expect to reject are rejected. And again, this looks like a giant blob of JSON. We've been over this. But the thing that I think is interesting about this is that we wrote code to generate the test vectors. So when we realized that there was another dimension in the possible multi-dimensional space of things that can go wrong, which, by the way, always has one more dimension than you expected, we just had to add another 4 loops around this and generate more vectors for the thing. And so we had all the vectors to test all of the combinations of the different things that can go wrong at the same time. And since that was code, the one that generates the test vectors, we wrote tests for the code that generates the tests. And so here is a test function, just a regular Go test that tests the vectors, which will generate the vectors, and then go over them and make sure that when used against certain specific verifiers that we know what they behave like, the test vectors cover the things that we expect them to cover. Now, you might think, isn't this a little overkill, Filippo? I mean, again, this is about high assurance cryptography, but the concept that I think is useful here is that we are doing software engineering to the tests. Tests are just data, like any other data that you generate and parse and validate and use. And the code that generates the vectors is just code, so you can test it. And you can do software engineering writ large, the general concept of software engineering, which includes testing and iterating on your tests too. We didn't throw away the code that generates the test vectors once we are done, because later we might want to add more test vectors, and it was much more convenient to do it while we still had the test vectors. And one of the things that are important about software engineering, I think it was Rob Pike or Russ Cox who said that software engineering is programming plus time. The other dimension of that is collaboration, open source. So what we did is we also published the vectors with a README that says what the different flags mean and when you would expect each vector to verify and not verify, and documented how you would use these vectors so that other people, just like we used the White-proof test, can pull in these tests and use them. And this works very well for things that have a spec, because of course everybody will want to be on the same page, but also can work inside your organization, because if tomorrow somebody needs to re-implement a piece of your architecture or needs to replace it and or rewrite it in Rust, they'll be very happy to have a set of test vectors that they can use and reuse. So we are sharing them as something called CCTV, which is the community cryptography test vectors. And the idea is to collaborate and centralize test vectors for all these different things. Another set of test vectors that I'm pretty happy about are the ones of TLS. TLS, you know, the thing that connects, does the handshake, certificates, HTTPS, the S in HTTPS, that. So we have a set of tests that will run the test against OpenSSL. So for example, this is a client test. So it will automatically start an OpenSSL server, and then run the test with this certificate and this key, and maybe these additional flags to OpenSSL to test different behaviors and things. But you can be like, well, that's nice, but what if you don't have OpenSSL installed? What this framework does is that it makes it easy for us to generate test vectors by running it against OpenSSL and then recording into the repository the handshake so that it can be replayed with a fake netcon to the tests that you can run without having an OpenSSL installed. And here my point is that there was significant engineering effort involved in writing the parser for this format and the framework that records them, but this really paid dividends, because when we break something, we immediately notice and the tests are very quick, while when we run them in generate mode, they take forever because it has to start OpenSSL, run the thing, shut it down, and who wants to interact with OpenSSL anyway? But the result is that since we made it both easy to write, because you saw how short the Go code was, and fast to run, this is how many we ended up having. And that happened over time, but once we had the technology invested at the beginning to make easy and efficient test vectors, we kept reusing it. Which brings me to the next point, test frameworks. The best things is sliced bread. And I'm not just talking about the test frameworks like Testify or anything like that, which we really don't use in the standard library. I'm talking about the ones you made for yourself, the ones you made specifically for your library. For example, we have this library called Acme. Acme is the protocol that you use to fetch certificates from Let's Encrypt, the free HTTPS certificates. And we have this package called AutoCert. It's a thing that just goes to Let's Encrypt, gets a certificate, comes back, installs it, does everything for you. How do we test that without actually hitting Let's Encrypt, the staging endpoint for every test? Well, we made a package called Acme Test that has a nice little CA server, which is a stub implementation of a server. It's a fake, not a mock. We didn't hardcode what it's supposed to do. It's just a tiny implementation that does just the minimum necessary. And it takes a testing.t. Because just like in Go, errors are values. I'm trying to make the point here that tests are just code. They're just software engineering you can do. And just like in that vein, you can have a package, a normal importable package, where you take a testing.t so that inside the CA server, if you see something that really shouldn't have happened, like the client really should not have called that API with that, you call t.error. And the error bubbles up to to making the test fail. And it has a bunch of nifty little things to make it easier for us to test things. And we use it, we made it easy to use, so you just start a CA server, you configure it by saying, oh yeah, accept this and this Acme thing and that Acme thing. And then we just take the URL, because it spins up an actual open port with the HTTP server, which you might remember, it looks a bit like the HTTP test framework, which if you never used, fantastic. It lets you spin up a HTTP server within your test that then you can hit with your requests to make end-to-end tests. And that's kind of a pattern, calling it name of my package test, which is the thing you use to test your package. And using it allows us to make these table-driven tests for things that were before just endless setup and tear down, that have things like this prepare function, which takes a CA server and just uses those knobs that we looked at earlier to configure it. So for example, this was a Let's Encrypt specific test, so it has a thing that says, hey, pretend to be Let's Encrypt, because we had some special case for reasons. And then it does some cache setup, and then the rest of the test is just the usual. And the result is that we went from an endless sprawling of custom tests here, which were redoing the same thing over and over and over and over and over and over again, to a very well-defined interface of the Acme test package, and then these just table-driven tests that are very self-contained and easy to add more. Because again, what's critical is making it easy to add more tests. And for that, I want to bring another example. This is from a personal project of mine. It's called Age. It's a file encryption tool. You use it, you generate a public key and a private key, and you encrypt some files, decrypt some files. Super simple. It has its own spec. Again, built for simplicity. This is the entire spec of the whole thing. It fits on 2 pages. But still, it has a lot of things that you're supposed to check. So what I did is build myself this little test kit, which allowed me to generate test files. Initially, what I did was just hack the Age program to generate weird files so that I could then decrypt them in tests to see if it failed or didn't fail and hit all the different edge cases. If you ever tried to get to a 90% or 99% code coverage, you know very well how you're like, how do I get there? Well, I was doing that over and over, and eventually I just built myself this little framework. And you use it just like a library, and use it in a function main. And you say, I want to make a new test file. It's a version 1. It has the file key encrypted with this public key, and then close the header with the HMAC, which is a format-specific thing, and then encrypt this message, and then generate it for me. And when you run generate, it spits out something like this, which is a small test vector that then can be used by the test suite. And the beautiful, I kept adding things to do weird and different things with this. So I can generate broken or correct or weird files all over the place. And then what happens is that I just have a test file which is much shorter. This is just 200 lines, which reads those files, and those files say something like expect success, or expect the header to be broken, or what to expect from that thing, and just runs them against Age. There's a bit of Go generate magic at the top, so that for every Go file that I create in a folder, if I run Go generate or Go test -generate here with the generate flag, because you can have flags in tests. Learned that from the standard library myself. It will run the file and put the resulting test vector in the folder. So it doesn't have to actually run the compiler every time. Again, it just pre-generates the test vectors. Nope, I keep tabbing off the... And the result is that I started writing tests for everything. For example, there's a place where you put a number in decimal. What happens if there's a 0 in front of it? Does it get accepted? Does it get rejected? I want a test vector for that. So I made a test vector that just encrypts with a password and the 10 value here, and then deletes the line and puts it back with a 0 in front of it. But sometimes if you parse 0, 1, 0, it gets parsed as what? Does anybody know? Octal, yes. And if it's parsed as octal, this will still fail, but fail for the wrong reason. What do? Well, we made it so easy to write tests that I just copy-pasted the file and made another one with 012, which is 10 in octal. And now either this one or the other one will succeed when it's supposed to fail, and I'll know that there's a bug. And the point is that I would have never spent the time to write that test because I would have been like, octal, that never happens. Spoiler, happened. But I wrote it because I had that framework. And since the framework is just Go, I could even import other libraries. I wanted a test to see what happened if instead of using the correct armoring algorithm, I used the armor algorithm from OpenPGP. Doesn't matter what it is. Point is, I didn't want to re-implement it just for my tests. I imported it because it's a Go file. So I could just write some code that generates the test vectors I want. And the result is that I wrote a lot of these. I started having fun. And the last time I had fun writing tests, this was the first time I was actually having fun writing tests. And honestly, this was the most fun I've had programming in a while, because when you write these test kits, they don't have to be perfect. They just have to be good enough to generate the test vectors. Nobody's going to use them, because nobody's going to build an application on top of my test vector generator. Nobody cares if I change them. I can refactor them every day to Tuesday. If I'm realizing that I always do it in a different way, I can make it easier. It's just the most joy I've ever had in programming in a long time, because I could just make it like I wanted it. And again, we go back to sharing back the test vectors. These are just the test vector generators are in Go, but the test vectors, you saw them, are just a small header and then an AGE file that triggers a bug. And so I put them up there together with the AGE spec, or in your case, maybe you put them there next to the implementation, and they found bugs in the Rust implementation of AGE. So this is a technique that I've mostly learned from the Go standard library, where there's a package in particular called test script, which makes this kind of things very easy. I wanted something even more specific for AGE, which is why I made my test kit. But there's this package called test script that you can import from Roger's re-exported version here, which lets you write things like this. Here at the bottom, you put a set of files that you want to have as part of your test. This is to test command lines, usually. So you can say, OK, create a file called hello.txt, then execute cat hello.txt, and make sure that the standard output contained hello world, and that the standard error was empty. And this is a test vector. And you can just make a number of them and make small variations by copy-pasting the file, just like we were looking at earlier. And we are doing that, too, to test the actual AGE command line. For example, here we run an encryption, and then a decryption with the same key, and make sure that it succeeds, and then a decryption with a different key, and make sure that it fails. And these are the files that are set up. If this sounds interesting, there's an article on the encore.dev blog that is where I've learned most of the details of this package. OK, so up to here, we talked about testing. And testing is great, and I'm clearly excited about testing. But testing is only about finding bugs that you can already imagine the input to cause the bug. Wouldn't it be grand if the computer just came up with test vectors for us? Well, that's fuzzing. And there's a whole talk about fuzzing tomorrow, which I'm very happy about, so I'm not going to go too deep into how fuzzing works in Go. But I'm going to mention that fuzzing in cryptography is at a disadvantage for two reasons. One is that coverage guidance doesn't work. Fuzzers are effective because they use code coverage to decide if they're doing something useful or not. One of the major rules of cryptography is that everything has to always take the same time. To take the same time, it has to run always the same code. That means 100% of the code runs every time, which means that coverage-guided fuzzing goes like, yeah, great, I'm done. And the other thing is that sometimes by just randomly generating inputs, you might not get to very specific edge cases that break programs. But that doesn't mean that it doesn't work. This is a project by Guido Vranken, I hope it's pronounced, which takes different cryptography libraries and runs them one against each other and with randomized inputs and checks that the outputs are the same. This is one of my favorite kinds of fuzzing. It's called differential fuzzing. And let me tell you, it finds a lot of bugs. These are all the bugs it found in cryptography libraries across the internet. It keeps going. I'm very proud of the fact that there is exactly 2 Go bugs in this list, and only one of them is a security bug. This being the security bug, which led to a whole, we should remove all of that code, which is happening in Go 120. But this was one of the security releases of the Go 117 cycle, which if you had to scramble to apply, apologies. Now, there is a thing we can do to make fuzzers more effective for cryptography. And here you might see a pattern. Taking these techniques and making them tailored to our specific use case. So, for example, here's implementation of the math behind Ed 25519, the Edwards 25519 package. It's basically just doing math, but with very large numbers, 255-bit numbers. You can't ask the compiler to do that. So instead, what we do is that we split it over 5 UN64s. That means we have to do carries. Remember doing math, pen and paper, and sometimes you would not carry the one, and the result was just all wrong? We do exactly that over and over, and you just stare at it, and you're like, the number is wrong, and I don't know why. It's a great job. I recommend it. So we wrote a fuzzer that's specific for this. So here is one of the fuzzed functions. It just checks something that we know needs to be true. So x plus y times z is the same as x times z plus y times z. Should be always true, right? So we give it random inputs and check if that ever doesn't hold, in which case we found the bug. But if we just gave it random ones, we might never hit the edge case of when it tries to multiply, I don't know, -1 times 0, and that's the one that breaks. So what we do is that every time we need to generate a random element, we flip a coin. If it's heads, we generate a random one. If it's tails, we generate a weird one. Weird means that we just draw from a set of values that we know are edge cases in our implementation. Now, this, you can't just port it to a different library, because this relies on the knowledge that our things are implemented with 51 bits of unsaturated. Doesn't matter what that means exactly, but, and the library is 25519. The 19 is 19. 19 is actually a number that matters here. So we took all the different numbers we could come up that are annoying to work with, but we don't really know what the bugs are. We just know that these tend to cause the bugs. And then we just gave them to the fuzzer to just randomly recombinate and see if it can make addition and multiplication not distribute as they should. And this worked. We did the exact same thing for the P224 implementation, which is just a different elliptic curve. Same concept, weird limbs here. I'm not showing it in the editor because this code is gone. It's now 100% safer. I've deleted it. And it found a bug that was reported to us without having anything about that bug configured in it. The person who reported it to us found it by running a fuzzer for hours and hours and hours until it got lucky. Ours found it in less than a second. because it was just throwing things that are known to be annoying at it until it hit the thing that was not working correctly. Okay, so this was about fuzzing, so making the computer generate the test vectors for us. But even better than finding bugs is not writing bugs. Captain Obvious. Well, what I'm talking about is spending time to think about the interfaces in your code. An example here is the Edwards 25519 API. This is the backend package of the Ed 25519 signature algorithm. We don't expose this in the standard library. You can't import it from the standard library. It's an internal package, which /internal means you can't import it directly. But it used to look like this, with a bunch of functions with no documentation that were just doing things and had unclear invariants. And it was fine because it was internal, right? We weren't making people use it. Well, we are people, and we were at the risk of using it wrong. So we went in there, and over years, we rewrote it to look like this. A type with methods and with invariants that are guaranteed and no way to do overflows or anything like that. All the docs, etc. Now, this is not about an external API, so this will not save anybody else from using it wrong, but it does help us not use it wrong. And one could give an entire talk about how to do that, but in general, the point I want to make is that spending time to make internal interfaces safe pays dividends even when it's your own interfaces. Then I also re-exported it as an unofficial personal package because people kept forking it and kept getting bit by the unsafe API. But anyway, it's still not exposed in the standard library. The next step in not writing bugs is, instead of writing code at all, is making the computer write the code for us. So code generation in general. One tool that I'm enjoying using a lot lately is fiat crypto, which is ungoogleable, by the way. You will get spiels about how Bitcoin is better than something else. I don't know. But it's a project from MIT that uses formal proofs, like actual mathematical proofs, to generate the kind of code I was talking earlier, the one with carries that might or might not fit in a Uint64. It has formal proofs that if you do these operations in this order, they will be correct. Now, the code it generates is not pretty. I'll not pretend this is pretty. But I know that the sequence of operations was generated by a computer based on a formal proof. So I just have to check that, yeah, this is correctly how you do addition. And then I don't have to worry about reviewing this code. And the code it was replacing, it was this, which was affectionately called in the industry the Christmas tree. It was passed down from our ancestors, and we didn't ever really question it. So we replaced that with the auto-generated code that we wrapped in a nice API with the begin interface that you would expect that calls into this formally verified auto-generated code. And the result of doing that was that the CL that did this had, ignoring the auto-generated file, deleted 900 lines of code that I had to review and understand and find bugs in, and replaced it with just 250 lines of wrapping around the auto-generated code. That required some tricks, which I've written about, but again, better to write a couple short functions to make the code that the computer generates work for us than the whole Christmas tree you were looking at earlier. Another case in which another code generator that really helped us is Avo, which allows us to generate assembly. Sometimes we have to write assembly. We try not to write assembly, but we have to write assembly to use particular instructions or to make some things particularly fast. And we use this tool now called Avo, which is a code generator where you write some Go, and it produces assembly, just like testkit produces test vectors. And that means that I can give things nice function names like add and mul and uint28 and shift right by 51, and then implement them by saying, oh yeah, use this instruction on these virtual registers that you keep track of. I don't remember what's in R13 and what's in R11. You keep track of all that. You're the compiler. there's a video of porting the assembly to that you can look up if you're curious. Okay, so this was all about how to write code. But the most impactful part of everything that I'm going to talk about is this last section here. And it's about reducing the complexity of what we write. The whole reason we managed to have a cryptography library with such a good track record, with much fewer maintainer resources than all the other, not all, but most of the other major cryptography libraries, is that we target a much smaller subset of what the other cryptography libraries target. We spend a lot of time saying no. And if I said no to you in an issue tracker or in a code review, apologies, this is why. So we have a number of policies to try to capture that. One of them is the assembly policy, which says explicitly, don't write assembly. And if you have to minimize the amount of assembly, and then use AVO, like we talked about, and write small testable units so that we can test them. And by the way, we want to be able to test it in our CI, because if you're using some new fancy instruction, we want to make sure that it actually runs in CI. More broadly, we try to follow what we called the cryptography principles. The idea is that the Go cryptography libraries aim to be secure, safe, practical, and modern, in this order. Writing it down helps because it gives you a framework to say no more often. Saying no more often means that you end up maintaining less code. Maintaining less code means that you write fewer bugs. So what this says is that we target specific subsets that are useful, but focusing first on safe APIs and focusing first on what we can keep secure. Part of how we do this is by deprecating things. Things that we don't want to spend resources on anymore get deprecated, which doesn't mean removed. The Go 1 compatibility promise is ironclad. Code never stops compiling. So we never remove something, but we mark it as deprecated. And if you use static check, it will tell you, hey, you're using something that's deprecated. And for example, Xcrypto used to have a lot of these legacy packages in it, like Blowfish and Cast5 and MD4 and Twofish. And if you never heard any of these, great. If you did and care about them, I'm sorry, but we're not going to maintain these. We're going to spend our resources writing tests for the other things. And we went through a number of these, including very recently in Go 120 Cryptolyptic, which we replaced with the Crypto ECDH package, which uses all of the things we talked about. It has code generation, it has fiat crypto, it has generics in there. I got an excuse to write generics. I really wanted to. They let me commit it to the standard library. I wasn't sure. Anyway, we said deprecating things, and then we reduce settings, for example. We try to remove knobs, and people usually get a little annoyed, but there are a number of things that we don't want to have to worry about, like the order of cipher suites. You might care about which cipher suites you use for one reason or another, but I bet that you don't care about which order they're picked in. And we can write code that does that, and if we don't have to worry about mixing the user preference, the application preference with the negotiation on the other side and what we think is more secure, complexity goes down. So we went in there and said, you know what? This option is deprecated. We're taking over that. And that happened, and nobody's complaining about it anymore. And and the result is that there's less complexity to manage. Now, how this will look like in your code is going to be different. It's always going to be different. But having a framework to reduce complexity and trying to stick to it is one of the things that worked the best for us. And finally, the most captain obvious of all, which should be the most captain obvious thing of all, but often overlooked, is making your code readable. Code is read much more often than it's written. Another very obvious thing, but a lot of software engineering is not done with that in mind. So for example, I made a point when I was trying to understand Poly 1305 to rewrite it as the most readable possible. with diagrams and functions that hid things that were complicated and panics that weren't necessary, because I know that never happens, but it helps you read along and understand, oh, that's always 0, so the next thing is safe or something like that. And I'm sure that these are a little slower than just inlining some of this, but we pay the performance cost to make it more readable, because making it more readable makes it easier to maintain and makes it easier to get high assurance about how it performs. This one I published as a blog post to try to make a point that especially when things are complex, like cryptography, you should make them easier to read, not harder. There's this sort of excuse that cryptographers use, which is, I mean, cryptography is complicated. That's why my code is hard to read. Should be the opposite. When I'm reading cryptography code, I'm already being like, okay, I think I remember how this works. But if I'm also trying to figure out what your bit shift does when it could have been a division, you're not helping me. I need all of that spare capacity because maybe I'm tired, it's in the evening, I'm on a deadline, something like that. Readability really paid dividends, and I know I keep saying that, but it's that forward thinking that helped us to think, okay, if we do this now, will it help us in the future? Speaking of future, there's a number of things that we're not doing yet. There's a number of things I would like to do. One technique I'm really a fan of is interface tests. If you define an interface, like netcon, you can write a test that just takes an interface, doesn't know anything about the underlying thing, and runs a bunch of tests about the invariance of it. Like, if you call write and the write blocks, and then you call close, it should stop the write. That's a thing you can write a test for that you can apply to all netcon implementations. And there's a package called nettest in nettest that you can use to test your netcon, and it's a free test suite that you write 3 lines of code and you have a full test suite. You just give it a thing that makes a pipe with 2 netcons that you implemented on the 2 sides. I'm a big fan of those, and I really want a crypto test package to eventually exist so that people can write their own crypto signer, which they do from time to time, and we can make sure that it does all the things it's supposed to do. Another one I think is really nifty is mutation testing, is a thing where the program goes through your code and deletes lines, for example, or changes things, and then runs the tests. If the tests pass, you're not actually testing that line. Even if it has coverage, if I can delete it and the tests still pass, and that would have found my white whale. This bug is a bug that I've been trying to write an agnostic test, one that does not know about this bug, but would have found it. And I've been trying ever since I've joined the Go team, because I found an exploit for that right as like a year before joining the team, and I've been trying to come up with a technique that would have stopped that bug from being introduced ever since. And I think mutation testing is it. Then there's OpenSSH integration tests, just like OpenSSL. I would like to do more of that. And talking of reuse, there's other libraries, cryptography libraries, that did the same thing, developed test suites that make it easy to make a lot of different tests. And I would like to take it and adapt them to rerun against the CryptoTLS implementation. So this was a grab bag of different techniques that we use to keep the cryptography libraries safe. I think that I was trying to make 2 points here. One is, here's what we're trying to do for you for the cryptography libraries so that they are a safe foundation for everybody, but also a number of techniques that you can use and ways to think about the investment in correctness that you can make in your own applications, in your own code bases, and how they pay dividends as time progresses. Because again, software engineering, programming plus time. Thank you very much, and if you have any questions, I'm happy to take them.
As always, raise your hand if you have a question.
I don't bite. The email is not there anymore, but I also take questions from via email, of course, but if anybody has one here. Are you going to get revenge for asking about tests?
No.
I'm not that kind of person. But do you know other projects or other platforms that are tested this thoroughly and like to this level of depth? And also, do you think cryptography is that critical?
Haha. Ooh, I like this one a lot. So the first question was, do you know other platforms or libraries that are tested to this level? And absolutely yes. I mean, much better than this. SQLite. SQLite has so many tests. It's incredible. It has test frameworks. It made its own programming language to write the tests and run them. It's amazing. Partially because it's used in avionics, turns out. But yeah, SQLite for sure. And then cryptography.io. The Python cryptography library that you should use, as opposed to the other one, has so many test vectors that half of the point of CCTV is to get them to move them into a thing where I can reuse them. It's kind of a plot. The second question was, is cryptography special? So cryptography hates you. Swift on Security once said that cryptography is math that cares what pen you use. And sort of, any small tiny bug in cryptography is probably defeating the whole point of having the whole thing in the first place. And this is not true of most of our applications. Like if you have a bug in your application, you want it to stay up even if it panics, because it will still be useful even if it panics, right? If my thing can made to be returned true in one little edge case and it's a signature verification, it's not any use at all anymore. So it's a little special in that, I think, in that it aims for a level of correctness that is usually not the baseline. There are definitely other applications that aim for that level of correctness or higher, but it's a field that enforces that as the floor. And the other thing is that we have a lot of specs. That's nice. It means we can reuse test vectors, and in theory, it means that we are supposed to know what everything is supposed to do. In practice, as I said, underspecified is the politically correct way to put it. But yes.
So you mentioned avionics, and a question popped in my mind about programs that are not allowed to fail, that are you cannot afford bugs in them. And so my question is, apart from the piece of paper that you can get from some certification process, but are there some techniques and that could be shared between high assurance software like, I don't know, you said avionics, I can say aerospace or whatever, or medical, because I worked in medical devices as well, that could be useful for cryptography and vice versa?
Yeah, it's a good question. I'll summarize it, tell me if I butchered it, as are there things we can learn from what avionics and other high assurance software does and reuse it as techniques for cryptography and for other software? There are definitely patterns to learn, and I always enjoy reading the SQLite docs, for example, about testing. I think a core difference is in the speed of development, because I am a security person, so I will, you would expect me to tell you that security is the most important thing and that everything else is secondary. But a very secure system that doesn't ship is not securing anybody. So avionics can afford to spend all of those cycles and slow down the release cycles so much to get all those additional assurances. It is important to know what level of investment you can have. Here, I've tried to focus on things that have high leverage, things that let you spend 10 minutes now to save an hour later. Avionics also invests in things that you spend 2 hours now to save nothing later, just maybe find another bug at the margin. The ideal number of bugs is actually not 0. There's this article by Patrick McKenzie, the ideal amount of fraud is not 0, which is the idea that if you made a bank that never had any fraud, it would be a terrible bank, because it would have to block you while you try to do so many different things that are legitimate. And so it's instead, it makes sense to eat some of the fraud to be usable. And there's a sweet spot, and some projects are way off in the direction, but I think here is the same. Cryptography, for cryptography, it makes sense to do all of these things, and even the most tedious ones, the ones that have less leverage, while for avionics, it makes sense to do the even more tedious, even less leverage things. For some applications, it will make less or more sense to adopt things, which is not a license to not do any of the stuff I talked about, because again, some of them are made specifically to make it easier for you to develop tests and to get to kill bugs. But there's a balance. So I think that there's definitely things to learn, but it doesn't mean that we should aim for we should consider a failure not to reach the same levels, because it's a costly, very costly trade-off. Which was also skirting the question, because I honestly don't know that much about avionics standards. I mostly know what I know from SQLite. Mostly fly planes, never had to write software on them. The ones I fly also have no computers in them, and I'm so glad that the engine will keep running even without electricity. Cessnas are cool.
So when working on the crypto package, especially at Google, what kind of working relationship did your team have with the compiler team? Did you ever have to worry about compiler and code generation bugs? And if so, how did you manage that?
Yes, such a good question. The question was, what working relationship did my team, the security team, had with the compiler team? And did we ever have to work around compiler bugs and vice versa? So sometimes compiler bugs would happen, and we would have to be like, oh no, is this a security vulnerability? And a couple times that way was. And that was part of our responsibility to decide if it is a vulnerability or not. But more interesting, I think, is when we would go to the compiler team and say, so we have this assembly. We hate it. We want to replace it. Here's what the Go looks like. The Go is low because it doesn't notice that, this is always 0 because it's been checked over here, and so it doesn't have to do the checks here, or it doesn't use the registers the right way. So here is why we have to write assembly. Can you fix it for us? And there are fantastic folks that did that a number of times. And eventually also explained how there is a long tail, which is a bit of a similar example to a similar team as the avionics testing thing, where there will always be a margin to be squeezed out by assembly, because the Go compiler is fast, and it only stays fast by not doing all the things. The Rust compiler is kind of slow, which I don't think is a bad thing I'm saying about Rust. I'm saying that it picks a different space in the trade-off. And so the Rust compiler, writing cryptography in Rust, sometimes is much less frustrating because you can just write it as it makes sense to you, and the compiler goes like, oh yeah, I move this here, here, and that I can eliminate because I know that from there, and great, here's 5 lines of assembly that do the thing. And I'm there being like, And then I have to write assembly. But still, the compiler team fixed a lot of these for us, and I've been very happy with some of them. One of them is that you can use hashes, hash.hash, without the value escaping to the heap now, because it will do devirtualization. So even if it's an interface, if you do h := SHA-256.new, it will know it's a SHA-256 implementation of hash.hash, and it will look inside that implementation, see that it doesn't do anything weird to the input, and so it can stay on the stack and leave its stack allocated. Might seem small, saves a bunch of allocations in the hot path. I have an article that if you Google APIs and mid-stack inliner in Go, which is all about how you can use a compiler smart trick that it learned to make APIs that are safer and easier to use, but still as fast as the more complicated ones. I'm very happy about that one. We started designing APIs differently because the compiler got smarter, and so we didn't have to make the APIs more complex just to make them faster. So happy about that one.
Last question? Okay.
Well, if nobody, sorry.
No.
If nobody has questions, and I will take a second to mention a thing about what I was saying at the beginning. Part of what I'm trying to do is to prove that professional maintainers can be a career. And so if you're interested in supporting open source and are thinking about it, either because your company is trying to do that and you have no interest in Go specifically, but you want to exchange ideas, we were talking about that earlier and it was a fantastic exchange, or because you have a lot of business risk on Go and rely on the Go cryptography libraries, let's chat. I'm trying to make that a thing because, you know, Log4j happened. I think people know about open source now. I'm just like kind of hoping that's right. All right, find me later. Thank you very much.